Thank you so much, Tatif. Just a couple of points. Firstly, the meeting is being recorded. Secondly, please keep your microphones muted so that we don't have interruptions. And thirdly, if you want to watch the last Open Mic Photonics event, we have it on our YouTube channel, and you can go there and watch it. And also, we have a photo contest for the public. So if you have any pictures promoting light and optics and colors in nature, in everyday life, and so on, please submit your pictures. With that, I would like to give the floor to Yousef to start his talk. Thank you, Yousef.
Thank you very much. Does everyone hear me? I believe I'm not muted. Yeah, Arash? All right then, I believe everybody else also hears me. Okay, I just have to, fourthly, after Arash stated, I'm starting at 5:13, so yeah, it's gonna take at least between 20 to 30 minutes, so I'm gonna stay in time. I just restarted my timer. Okay, hello everyone, and thank you for joining me on my presentation about my journey as a researcher from Iran, as you can see in the pictures. As my holograms evolved, I also evolved. I guess I also evolved a little bit. So we're going to talk about that today. And this is going to be mostly through the scope of my project on digital holographic microscopy. And I would like to thank the B-Phot chapter that gave me this opportunity to share some of my experiences and obviously get some feedback on the decisions I made and the actions I took in my scientific life from my peers. Now, the title begins with "From Iran," but the real question is, where are we actually from? The only place that a researcher is officially required to explain to their peers about where they're from is their affiliation in the papers. Now, according to the last paper that I published on holography, I have two affiliations. One of them is from the University of Zanjan and the other one is from the University of Tehran. Which are located in two cities at about 5 hours apart in Iran. But this is not going to be my version of the tale of two cities, since most of the project was done in University of Zanjan. So I'm not going to talk about my experience in University of Tehran in this presentation. And I'm just going to talk about the holography project that was done in University of Zanjan. And first of all, before I begin my story, I should strongly emphasize that this is just my story, and people can be from the same country, the same university, and hell, even work with the same supervisor, and yet have a completely different experience. So just like the leaves on a tree, people may belong to the same one, but have a totally different story to tell. So I would like I know for many Iran is really a black box, but believe me, it's very difficult to generalize anything there. Now, back to the story. I started my academic life in mechanical engineering, bachelor, as a student in University of Zanjan. Now, when you search mechanical engineering on Google, I actually did it for this presentation. This is what you see. Handsome guys with serious looks and fancy machines. I was more like this, a bit fat, nerd looking, bottoms tied up to the neck, no tie, and checking a picture I just took from the test configuration with my Nokia 5530 for publication. Now, I believe that these phones are out of order recently, but before I start my serious academic work, long before this picture was taken actually, which I couldn't find any picture from that time. For a while, I was just trying to figure out what I'm going to do in university as an academic and how I'm going to become a scientist. I was literally knocking myself to this wall and that wall, from trying to figure out how Kepler realized the motion of planets based on his tables of data of the planets in the sky, to trying a failed actually attempt to study a second bachelor degree of mathematics concurrently with my mechanical engineering, which, by the way, I have to say I felt quite a promising candidate when I thought that I realized by myself that the number of points on a semicircle equals the number of points on a line, only to be disapproved by my general mathematics professor that actually there are no number of points in that, and he showed me that this is something they are studying in the first year of their mathematics course. So I was basically naive, young, and trying to focus my energy into something. And from those years, when I look back, I just learned one lesson, that as a scientist, or as in life and in science, I should do something that matters for me. I mean, it is easy to let our ego decide for us without considering the value of ourselves, the time and the energy we spend on something. But in the end, it should be worth it for you on a personal level. Now, I can hardly go back and tell my ego-boosted youth self, and to be honest, for that matter, to any ego-boosted youth. But as I'm reaching my middle ages, I'm sure that in many ways the crowd are also reaching their middle ages. I like to remind myself how, in my opinion, being a scientist was being able to do math or to do something related to astronomy. A trap that I might fall anytime I see a colleague or other scientists working on a space telescope or a project that I might consider fancy inside myself. So this is a lesson that I would really like to take from those days, and to understand that science is not about having etiquettes on your project or what you do. And you shouldn't let your ego decide if what you're doing is actually science or not. Now, back to the picture that I've shown you. The device that you're seeing in front of me is a 3-point bending test device. This is how it works. If you model it in finite element, this is how you would see. You put a beam there, there are 3 points, the third point in the middle is coming down and bending the beam and performing some stress. Now, I was working on this device based on my bachelor project. It's not yet holography, but this is what leads to the holography project. I was, for my bachelor project, working on sandwich materials. Sandwich materials are materials where they have 2 stiff faces. You can put 2 aluminum layers, and in between there is a flexible core, like PVC foam. Now, PVC foam by itself doesn't offer any resistance, but when it is sandwiched, it improves even the capabilities of these stiff aluminum faces. Look at this picture, for example. You see that there's a lot of stress on the top layer, but the bottom layer doesn't experience that level of stress. There's nothing red, no pixel is red on the bottom level. So it means that, for example, if you're sitting in a tank or an airplane, if there is a sandwich material covering you, the layer inside is not going to experience the same level of load and shock and vibration that the outer level is. So that's why you can sit on an airplane and have fun without understanding any of the vibrations that coming with you from the wind and the von Karman and every kind of disaster that's happening outside the plane that you're safe from. So I was studying this project, this bending, based on a fringe projection technique. It's a very simple technique that you use an LCD video projector. You project a few parallel lines, which we call them fringed, into with an oblique, of course, angle to a specimen. And as the specimen bends, these lines do bend too. And by taking a picture of that, you can finally analyze that picture and find a 3-dimensional profile of your bending. But how did it all start? How did I even start considering doing anything with optics on mechanical engineering? It started all with a seminar about Mare. It was in physics department that the seminar was. I had some friends in the physics departments, and they told me, hey, let's go there. We have nothing to do after lunch, so let's go sit in that seminar. And I said, why not? Let's go. The seminar happened to be given by Dr. Rasuli from IASBS in Zanjan. It's another university in the city of Zanjan, which is focused on master in science. They don't get any bachelor students there. And here is him taking an ICO Galeano Denardo Award in 2009. This presentation was before that. He had a seminar about Mare technique. Mare technique is when you have 2 of these fringes, these parallel lines I talked about, and when you put them on each other, you see a third pattern showing up, which is moving much faster and much larger than the original pattern moving. So, for example, if this moves 1 micron, these big fringes move about 1 millimeter. So it can have even 1,000 times kind of magnification of movement. So I was just fascinated by this. I mean, I then just couldn't stop, and I went forward after the presentation. I said, can this be used in mechanical deflectometry? We want to measure the deflection of different samples and materials. Can we use that to make these measurements with much less expensive equipments like fancy extensometers and stuff? And his answer was yes, of course, and it's a common method. Now, so there was a seminar, there was a question, and then there was a girl. So this is Pega Asghari, that time bachelor student of physics, and she's my ex-wife. So back then we were just dating, and she had a optics professor, Dr. Alireza Maradi from University of Zanjan. He was teaching optics to her. So I made a connection with Dr. Moradi through Pega, of course, and we talked about the possibility of using this in mechanical engineering. And he happened to have a lot of experience with Maury technique in general, and with fringe projection, very limited, but with Maury technique in general had a very good experience. And he was quite enthusiastic about it. Now we had to find my professor from the mechanical side. So I was having mechanics of materials, and I was so lucky that I got it 1 year late because I was behind the list. I didn't wake up soon enough to get that course in the second year, so I had to pick it up on third year to advance on other courses. So exactly on that year, he joined our university, Dr. Omid Rahmani, Mechanical Engineering Department of University of Zanjan, and he started teaching mechanics of materials, and he became my professor in that course. And the part that we got really lucky with is that these two ended up to be old pals. They ended up to be very old friends to each other. So they knocked up in the first meeting. It's very good, just matched up. And the whole idea started, and we started working and working and working. And in the end, even it ended up in publication. Right here. So based on this project of using Maury fringe projection to study composites and sandwich materials, we had first made the first connection. When I look back, I see that this was a child of different causes. First of all, there was no systematic mechanism in our university to define these projects. So I could freely sneak anywhere. There was no grant application, no nothing. It was a chaos. And I really used that. It was good for me that there was no such thing happening. Second of all, we had two young and ambitious and, to be honest, very cool professors. And that really helped. They met up, they were enthusiastic by the idea, and they followed up. And I was so lucky that both of them were hired by university recently, and both of them were who they were and knew each other from before. And when we see a chance, we should seize it. In this case, I actually seized the chance and I didn't let it go, didn't let it slip away. When I heard that it was already done before, I didn't discourage myself, but I actually encouraged myself that this means that this is actually not a stupid idea, so maybe we can do something about it. And of course, there's always a girl. Now let's go to the digital hologram. Years has passed, a couple of years has passed from the projection project, and we had a publication submission. We had the trust of the faculties, both faculties, that this mutual work can actually lead to something. It was I think it was the third year of my mechanical engineering course, and we had this metallography course. Now, what is metallography? If you want to explain you in very simple language, I don't know if Pedram is here in the audience. He knows a lot about this, our colleague in this project, we'll get to it. You take a metallic sample, like carbon steel, normal carbon steel that you use in your buildings. A sample mostly shaped like this. And you start polishing its surface. First of all, with a 400 grit sandpaper. We mostly polished with hand underwater with different directions. It's a very time-taking and painstaking procedure, to be honest, if it's not done automatically, which we were actually doing it manually. 600, 800, 1,000, and then 5,000. You would be able to see yourself in it. It would be almost like an optical mirror. And then you etch this surface with a weak acid. If you put it under a microscope, these two pictures are likely what you're going to see. These two pictures are from the plain carbon steel. The white area is called ferrite, which is only Fe crystal. And the black part is a combination of ferrite and cementite, which is Fe3C. It's the bond between carbon and Fe atom. Now, you know steels by their out behaviors, hardness, stiffness, by their macro behaviors and strength. If they can stand more load without deformation, if they can stand the load after deformation and not break, or if they can be scratched easily or tooled easily, or no, you need to get an actually a strong tool or an HSS tool to be able to make a hole in them. But these macro features have also meaning under the microscope. From this picture, from the size, shape, and the statistical distribution of these black areas, you can find out from their dimension, shape, and everything, the carbon percentage, and all of these macro properties of the metal. So we learned a lot of stuff from this simple microscopy image. It's a common practice that metallurgists use. But then I thought, what if we could see it all in 3 dimensions? What would happen if we could actually have the same picture, not like AFM, just inside one of these black areas, very, very low, no, the full image. You see, this is 300 microns. And especially in my country, AFMs don't have that much, at least it's not easy to find such good AFMs that can give you a picture like that. What if you could see in 1 second, just like the microscopy, in a second, this sample in 3 dimensions? Well, I had another project to build and I had another recipe to make. So we had the optics professor already. He was Dr. Yousef Pourvais. We knew him from the previous project. He trusted us, so he knew that when we have an idea, it possibly can be stupid, but there was a chance that it's a good idea too. And he would guide us to do the proper literature review and to present the idea more maturely. But we needed a metallurgist. For metallurgist, we couldn't go to Dr. Rahmani anymore because he was expert in non-metal composite materials, in polymer materials. We needed someone who has expertise in metals. So again, I was lucky and I had this metallurgy course with Dr. Hamidi from Mechanical Engineering Department. And on the second course I had with him, I did a really good CAE finite element project based on what I did for the composite project. I did a roller bearing for him on the finite element design, and he actually trusted me a lot. So I went to him with this idea and he was super enthusiastic. He was super cool about it. And he told me that he has never seen it being done ever somewhere. Now, he was someone who studied metallurgy in Bologna and other places of the world. I kind of trusted him at that point. But when I talked to Dr. Moradi about this, he said, relax, you should do an extensive literature review. It is unlikely that nobody has ever thought of putting a laser on a metal and getting a hologram. It's really unlikely. Then the third part of the recipe was to find a method. Now, again, here I was so lucky that Dr. Moradi had a digital holography set up in transmission mode for biological applications. For example, this is the setup that he published on seeing the myelin figures on lipids. He was studying basically 3-dimensional shapes of lipids and how they form these myelin figures in different conditions using holography. So we just had to turn this, from transmissive to reflective, which ended up to be a 3-year project. And this time, again, a girl, of course, my ex-wife, Pega, and also a boy. Pedram Abdullahi was a master's student of Dr. Hamidi, and he entered the project and he helped us a lot with sample preparation, with the studies we needed to do on the samples. We needed someone to devote his time on the metallurgy part. And I want you to see this whole lack of structure in this thing too. When in B-Phot, when we define a master thesis or a PhD thesis, it's really a different procedure. Funding should be considered, applications should be considered, but there it was just a decision made by the supervisor and made it quite easy and made it quite brittle, to be honest. So our initial setup, we went for a Michelson interferometer. Basically, if you don't know what's a Michelson interferometer, the light comes from the laser with a beam splitter. It's divided into 2. One part goes to a mirror. It's a reference, goes to the camera. The other part goes to the sample, comes back, goes to the camera, and this reference from mirror and sample light from the sample interfere together and form these diffraction fringes, these interference fringes, holographic fringes, and based on that we can see the 3-dimensional structure, something similar to what we saw in fringe projection, but on a different scale of optics. It's a wave optic phenomenon. It's not a geometrical optic phenomenon anymore. Details aside, we also matched it with a white light microscope because we wanted to first see where we're looking at and then get the hologram. Now, we did the literature review, and day by day, we understood that we apparently hit the bullseye. The only reference we could find of doing holography on metallographic samples was that they polished the surface, got a reference hologram, Then they heated up the sample, the same sample, without moving it from its stage, and they had a sample hologram. Now, what's a reference hologram? All these parts here have their effects on the light, have their effects on the wave optics of the light, so have their effects on the fringes. In order to remove all those effects, you have to remove your sample or put something exactly in the place and orientation of your sample, exactly in that spot, that has no features. It's like a mirror. Imagine if you had a very, very accurate positioner that could put the sample in the exact orientation and place that it was, and remove it and then put the sample again. You first get a reference hologram and then you get a sample one. What we did was that we had the sample polished, and it was this brilliant idea that we etched our sample only halfway. Only half the surface was etched. This part we used for reference hologram, and the other part we used for sample hologram. Our initial holograms and our initial setup was an absolute disaster. This was the initial setup that we had. This beam splitter that you see here, we had to borrow from another master student. So every time, so one of the reasons this was really not good was that every time that we wanted to test, we had to borrow back this beam splitter, align it, and check ours and do our holography again. So we started with a very, very weak hologram. At that time, we were accepted for our first basically foreign conference in Yerevan by the SPIE student chapter in Yerevan State University, and the Russian Armenian University. The trip to there was 22 hours on a bus, plus 2 hours of border control. So we were really drained when we got there. This was the poster that we prepared, and maybe I can say that as a result of that long trip, we missed it in the taxi on the first day. So we had to ask Tatev to help us to print a poster in Armenia, which she was really helpful with that. And that really was probably the first time that we bonded our friendship back there. Well, our holograms have improved by then, by the time we went to Yerevan, of course, and still not really promising, but we at least could see something three-dimensional that is representative of the two-dimensional picture that we're seeing. But it was obviously a work in progress. I was also a work in progress. I moved from this to this. So I don't know about you, but between these two, I can see some improvement. It was a really amazing trip for me, and it's really answered a lot of my questions that I still was carrying with me as a youth that tried to figure out science. I had my first napkin moment with Professor Rhodes. We were talking about something. He just gathered first a napkin. I don't have the picture of the napkin, unfortunately. He first gathered a napkin and wrote this setup on it. I think it was about we were talking about tychography at that moment, and he was saying how he would think we could do that in transmission and stuff like that. I don't actually remember. And then he later on the next day put the napkin beside and wrote it on a paper. So this was one of the things that as a youth I thought that scientists, if you have it, you're considered a scientist, and if you don't have it, you're not considered a serious scientist. The second part was that I was called being a scientist by so many legit figures like Professor Dennis, Professor Berry, like Professor Rhodes, and it was really something big for me. In their mind, they were just calling me by my job. In my mind, they were calling me by my dream as a youth person. So that was a big deal back then for me. And it was the first time I met an Israeli scientist. And for somebody who is from Iran, Israel is always seen through a propaganda, either the anti-governmental propaganda or the pro-governmental propaganda. But this was the first time I was talking to actually someone from there, and I realized one thing, that it really doesn't matter where we're from at some degree. We talked for about an hour. We hardly talked anything about politics besides from daily life, how it looks like there and here. And it really reminded me of this BBC journalist's memory. He said that in the midst of the Serbian war, I was hiding behind the bushes, and all of a sudden somebody showed up. And I was afraid that from which side he is he going to kill me or not? I asked him, are you a Serbian or are you a Muslim? He just looked at me in the eyes and said, I'm a musician. So that was really, for me as an Iranian, was really a hard proof of that probably is also held for scientists, that is also a measure that we can agree on that exists for the scientists too. And I was, for the first time in my life, confused with a British person and the French person, because if you see, my family name is Pourvais, but this is the way I write it because I don't want to write poor and vase as something that you keep your flowers on. So somebody showed up and said, are you French? And first he started speaking French to me. I was like, what? He just said, are you French? And I said, no, thank you. So all these experiences were really something that boosted me up. The effect of that boost was that we immediately worked harder, better in the lab. We negotiated a week deal with that master student so we can have the beam splitter at least for a week and then give it to her for another week. So in the end, our holograms have improved a lot, and we decided, based on the study that Pedram and my metallurgy professor did on stainless steel, to study stainless steel corrosion. Now, this is the picture that you see of in stainless steel on the microscope after that etching procedure. At this stage, stainless steel is so hard to polish and etch. It's not like the carbon steel. And it takes at least, I think, 20 minutes to half an hour. Pedram was doing most of this, and because we didn't have a space, he had to do it in a bathroom sink. So he would cut these sandpapers into pieces, put them on the bathroom sink, open a mellow cold water, and start polishing for about half an hour, and they will come downstairs, put it on a microscope, and we could see it together. Our holograms, Yousef, as a result of... Yes?
Yousef, you've got 5 minutes.
I know, and it's going to be finished. Don't worry about it. Our holograms has also improved. This was our reference hologram. As a result of Pedram's polishing, which was a critical step, we had very good mirror-like pictures, the best we could get, and our sample holograms had a very better field of view. And I have also improved a little bit at that time. Not much from Yerevan, but in a couple years after that, I think I improved a lot. And this is the only picture I have of my presentation awards, actually, which was given in Italy a couple years after. I think it was 1 year after Yerevan, I believe. 1 year after Yerevan, and this was the time that we really were thinking of publishing something on stainless steels. Well, our 3D images was pretty good. For example, you can see the 3D image we took from this area. Not really definitive like AFM, but look at the scale that we got here. And finally, I contributed something theoretical to science, which was a fetish of my youth to have some theoretical basis, add something theoretically to science. Because we were able to see this three-dimensional surface in a much larger area than AFM was able to see, we could define statistical characterization of stainless steel corrosion. We called this parameter step, which means if the grains are forming a step, and this one was ditch, which was the corrosion that happened in the boundary of grain 1 and grain 2. You can see them on the picture qualitatively too, but we provided a quantitative parameter for that, and we could for the first time quantify this factor. In the ASM standard, ASME standard is mostly written by qualitatively. You look at the picture, if none of the grains are fully surrounded by a boundary, you call it step. If it is surrounded, you call it ditch, and there's nothing in between. But as we quantified it, we could compare really the effect of, for example, annealing temperature on the step and ditch parameters. And as you can see on the first picture, we have 88 step, 24 ditch, but in the other ones, ditch and step are becoming more and more equal. We got rejected 2 times, to be honest. The first one was really a long shot. It was the highest journal of metallurgy, which really didn't help us because they didn't provide a good review because they rejected us right away. The second one was really helping us. The review was 2 times reviews and then rejected, but they really improved the paper. And on the third one, after 3 resubmissions, we could finally publish that. And the reviewers for us were from another planet. They just right away told us you have 2 months to provide an AFM image of the exact same area that you get the holography to prove that your technique is working. Beside the fact that it was hard to get an AFM, I had to go to Tehran to another university. How can you find this in that? This is the microscopy image that we get from the AFM device, and this is the AFM image that they give us. Look at it in the big scale. How can we supposed to find a structure here that looks like this? Well, here, Pedram was doing his military service at that moment, so he wasn't even working with us. We were chatting in Telegram. Apparently, he had a phone somehow on service, which he should explain why. But he found the area. It took him, I think, 1 hour. He found here. He said, yeah, right here it is. And he was right. It was there. We compared and everything worked out. And something that was really bound to be a big challenge was solved by someone who were not even in the team at that time, and he was doing a military service somewhere. And after that, we went for our second publication, which was about telling the photonics community about this new line of research, that you can use this if you know holography. Metallurgists are eager about it. They don't know about it. It's time to start that line of research. And for now, it's got about 3 citations, that paper, between all the papers. And it was funny because a few months ago, well, years ago, actually, it was before pandemic, 1 year and a few months ago, there was a scientist from Cuba, I think, coming to visit. And he was presenting with me and Heidi, and he mentioned our paper there without even knowing I was sitting there. And it felt really good that we finally has showed that to the scientific community. Now, this is going to be basically my last slide, and I'm going to have 1 minute overdue for that. Having this story, I would like you to think with yourself about your life, all decisions that you made and actions that you took. That, how do you define where you are from? First of all, it's good to notice that science is much more than just data and publications. Our brain, our imagination, our mentality, these are our only tools. It's like we are workers that instead of hands have a brain. And often we use them to their limits. So your life story, I believe, as a scientist, is worth of reviewing once a while to make better decisions for yourself, for your brain, which is your only tool of work, and for the future of you and your group. And just to end my presentation, I would have to tell you that the story of the second city is a completely different story. Maybe we have one day the chance to talk about that too. I don't know if I have to thank you at the end of presentation based on what we said with Tatev or not, but thank you very much for your patience.
Thank you so much, Yousef. It was a great presentation, amazing details, a very, very nice story. Now we have a couple of questions in the chat box already, and I would like to ask Luca to unmute himself and ask
every question personal. So
all right.
Yes.
So it was at the very beginning of your presentation when you presented your bachelor in mechanical engineering and your interest in optics and astronomy. I was thinking that if at that time, did you consider a bachelor in physics or maybe a master in physics after your bachelor in mechanical engineering?
Well, that's a very good question. My story was very much sunshine and butterflies. To select mechanical engineering wasn't a choice that I was given that much, with that much freedom. Back in Iran, our family was not in a situation to support a lifelong of scientific quest, so they really wanted me to get a degree that, in their opinion at least, would get me a good job. So I was given a choice between not all, but these engineerings: electrical engineering, mechanical engineering, and civil engineering. Electrical engineering, I was dumb, I'm still dumb in it, so it was off the table. Civil engineering, they didn't have a good reputation because buildings in Iran suck. And I was 18, okay? So this is nothing logical to an adult mind, what I'm talking about. So the third option was mechanical engineering. It was good. I know the cars in Iran suck too, but, you know, it was the best of all options. But yeah, when I went to university, no, I didn't consider myself having a second bachelor in physics. I considered myself getting a bachelor in mathematics and becoming a genius in math. But then later when we met friends from physics and I saw the actual applications, I didn't even know optics exists.
Oh, okay.
To be honest. No.
Okay, thank you for your answer.
Absolutely.
All right, and we have a question from Rohan. Could you also please unmute yourself and ask your question?
Hi, Yousef. Amazing presentation. My question is that you had inspiration from mechanical engineering and then you contributed to optics. So do you feel learning photonics can help or enable a student to contribute to different fields?
To be honest, I consider what I did a contribution from photonics to other engineering. I'm talking as an engineer now, okay, with bias towards engineering. Let's talk this way. Photonics is truly an enabler. A laser by itself and holography by itself and this projector by itself, yeah, may not matter that much, as you said. It may look like it's a contribution to photonics, but the whole paper was about that projector and what it did. The part about bending was all known and all done by engineers. We couldn't publish just the bending part, absolutely non-publishable. The equation we used were 40 years old. But we were the first one who could see it with such speed, at such level of depth and intensity. We could see the difference between the actual equations and that. So I will consider it mostly photonics enabling engineers to see the stuff that they didn't see, but you need engineering insight too. That was why for the first project, I learned my lesson. I searched for 2 colleagues from engineering department and not putting myself to behold that thing by myself.
Well, thank you very much. I feel that I had a similar path as well. I'm from an engineering background as well.
Really? Which engineering?
Engineering physics.
Okay, nice. Good luck.
Thank you.
All right, we have more questions. Tatev, can you please unmute yourself?
Really? I'm in the bus going to train station. So, but my question is like, if someone asks you now your affiliation from where you are, what is your answer then?
It takes 30 minutes to answer that question, Tatev. That's what I'm saying. It's as a scientist, at least, it's not that easy to answer that question. You can be from the same country, same institution, same professor, but yet have a totally different story to tell. So you may answer with your affiliation, but if you want a really true answer, I believe you should look into your life and answer people.
Your answer now is?
B-Phot, apparently, right?
Okay. Yeah, I expected at least like Belgium, Brussels, but B-Phot also feels nice.
I don't speak French.
But he speaks B-Phot. There is another question from Natalie. Natalie, could you please also unmute yourself and ask it yourself?
Yes, hello, Yousef. Thanks a lot for this very original presentation, a very different point of view as compared to typical presentations. So it's really, yeah, very interesting to see. And so my question is actually, it's a kind of follow-up question on the presentation that you just gave. Like, when did the idea really came into your mind of going, in this case, going to B-Phot for doing a PhD in photonics?
So let me explain shortly, but summarize the whole stuff that happened. First scene was when we went with this idea to a aerospace conference back in Iran, and everybody who was visiting our poster and was interested was a military official. And I realized that if I continue this path, the #1 contender of using this advanced materials is military officials, which is not a bad thing. I wasn't comfortable with it. So I thought that between bullets and band-aids, I'll need to provide the band-aids. So I decided whatever I do, it will be in the field of biology, not in the field of industry anymore. Again, young mind, youth, stupid, whatever. I kept that in my PhD applications too. I didn't apply for any PhD positions that was not biophotonics, no industry. It was hard a little bit because I was a mechanical engineering bachelor, and I never had a physics degree except a master degree, which my marks were not that good because it was the tale of the second city I'm not going to get into. But yeah, so I decided first to go to bio, and then between biomechanics, let's say, which was completely off my mind, in biophotonics, I saw the power of photonics in enabling engineers to do stuff. I saw that with a simple link with anyone in photonics, you can make them a better scientist and make that field a better field. So I was sold. By the time that we were on the holography project, I was sold to photonics. I even took a Fourier photonics course in the last year of my bachelor, just sat there to learn about Fourier optics. And B-Phot, Tatev. Yeah. Tatev and Heidi. About B-Phot, Heidi came to Armenia once, gave a conference. I loved the manufacturing that you did there. As a mechanical engineer, I was fascinated by the level of precision molding that you were doing. And when I was searching for a PhD, Tatev suggested, hey, we have a position, would you like to? And well, yeah, of course, I'm interested. Yeah, why not? And yeah, it worked. Yeah, that's the beauty of networking. Indeed. SPIE chapter. If you're not a member, become a member today. Thanks a lot. Thank you very much.
So I also have a question until somebody else puts a question in the chat box. So you talked about the approach that you had in Iran in finding ideas and in working on projects and so on. But you're now in B-Phot in Europe, in a Western country. Can you make a comparison between what happened back there and what happens here, like usually?
This is the overview of the recipe for a project that I kind of followed with both projects that I did and led to publications back there. I tried this recipe in University of Tehran. It failed miserably. I finished my master thesis almost getting fired from university. I finished my master thesis in the 3rd year of my bachelor. So what I'm saying is that looks amazing, looks like sunshine and butterflies, but it doesn't always work. A system always works better. You can be more patient, you can follow grant ideas, you can be patient until you get your PhD and then come up with ideas that are eligible for grants, or you can go the American style, which is their style I'm not going to talk about, or you can go the Iranian style, which means that if you're lucky enough to find the right people at the right time of their life. You see this guy here? He is the father of optics of Iran, Professor Tavasoli. He was my supervisor in University of Tehran. But he was too old and the government put him under so much pressure that he wasn't able to have that enthusiasm anymore. The government has retired him by force because of some political problems. So I still believe that between the American system, the authoritarian system in Iran or other countries I'm not going to talk about, and the snail maybe, but efficient system of Europe, I really suggest the system of Europe. You have a path that you know that will lead to certain answers.
Thank you, Yousef. If there is no more questions in the audience, is there? If there is no more, I'm going to ask one more. So, as we've seen here, you have brilliant ideas. Sometimes they hit, sometimes they miss. Has that? Yeah, that's the way. But has that continued to here? Like, have you had any experience here at B-Phot that you had like, oh, this crazy idea, and you tried it out with some out-of-field people and it worked?
Yes, but I'm gonna go back to this slide again. I may have thousands of ideas and my ego wouldn't let me leave my project on holography and think, I did all that, why don't I continue it? Why don't I talk to someone about it? But in the end, you should see if it matters for you. Now I'm in a team with a certain system, with a certain policy of research. If I have a creativity power, if I start now talking about this and that wild idea, it will be like studying Kepler project all of a sudden in my bachelor course. It has nothing to do with my background, has nothing to do with my scientific future, or we like studying math again. In the scope of a PhD student, I believe it's good to have creativity, but better channel it into the research policy of your group too. Otherwise, you will end up with a grass field instead of a tree.
That's true. That's true. So if there is no more questions from the audience, let me check the chat box again.
Don't be shy. It's okay. Ask questions. Yeah.
Tattoo is saying when he writes tattoo, you know, when he gets the idea. What's the story behind that?
Well, sometimes when I have ideas in the scope of the project, we talk to Tatav about the twos. And yeah, for example, one of them is in my commission, I had these long shot ideas, which I didn't present in commission, but I presented to my own supervisors. But when presenting those long shot ideas, like combining Raman spectroscopy with a stochastic image analysis to improve your signal, it's a really good one. But step by step, you know, don't go Kepler. Don't go all Kepler on us.
All right, that's great. That's great. Thank you so much again, Yousef, for your amazing presentation and an amazing Q&A session. Natalie wants to say something. Please do.
Yeah, perhaps just a small comment, Yousef, on your last remark. maybe you have heard about the Friday afternoon experiments. You know, it's something that in B-Phot happened a couple of times, that if you have some idea and maybe it's crazy, but if you can try a first test on one Friday afternoon, then you just lose a couple of hours if it doesn't work. But if it works, then maybe there's much more future into it. So
okay.
Sometimes I do it on a Friday afternoon when you really say like, okay, I have a couple of hours left. Why don't I just give it a shot? I'm not saying that you have to do that every Friday afternoon, but once in a while, it's fun.
Yeah. Is there a system to apply for this, or is it something official in the systematic, or you just do it?
Yeah, you just do it. I mean,
okay, that's nice. That's nice.
I hope that I won't be upsetting your supervisors now.
Okay, yeah, you said it. I didn't say it. You said it. I have this stainless steel sample from back in Iran, and I would really love to regenerate some holograms to see what it looks like here with the objectives and the because it's important in Mic Photonics to have a big beam splitter. Otherwise, you wouldn't have fine fringes. So maybe one Friday afternoon after pandemic. Right now, it's not possible for the reservation and stuff. Maybe, why not? I still have my samples, so let's see.
Well, if it can be done on a Friday afternoon, as I said, risk is low and potentially there's high gain.
Yeah, sure, definitely. And probably Raman spectroscopy of this, because we talked also with Malina, the intern that we worked in. She was a metallurgist. And we were talking about how these black areas on the metal can have a Raman signal, and apparently nobody thought of studying that yet. These parts. You see, the metal itself has no Raman signal, but Fe3C has. And the Raman signal of this can say us plenty of information about metal that we cannot have normally. But we'll see after pandemic.
From now on, the Raman will always be booked on Friday afternoons.
No. Okay.
Amazing.
Oh,
amazing.
Great. Wow.
Just don't explode the biophotonics lab. A lot of lives depend on that.
This is steel.
Yeah.
Explosives.
Safety first. Safety
first. Amazing. Thank you so much, Yousef. And we are right in time to close the session. So in the end, I would like to ask everybody to turn on your cameras, please, and for Yousef to stop sharing, please, so that we can actually take a group picture of this event. Asrik, would you please take care of that?
Exactly, but please, everyone, switch on your cameras and wait a few minutes, but that I will take a few screenshots, okay?
Amazing.
Smile. Yes, and more people are joining. Yes, okay. 1, 2, 3. This is the first one. Okay, another one. Oh, what is that? Okay.
Tata is in the train.
With Sergey.
Thanks a lot. And I would just take one last one, please, because now more people are joining. So, okay. 1, 2, 3. Where I am. Great, thank you.
Amazing. Thank you, guys. Thank you so much for coming. Thank you so much for listening to Yousef. It was an amazing presentation, Yousef, again. If you want to actually present something in Open Mic Photonics, we have 2 slots open in mid-April and mid-May. So please tell us if you want to present something. And also don't forget the photo contest and our YouTube channel and social media. Thank you so much. And
Arash, one more point. I think that even the people who are not from B-Phot can feel welcome to, if they have an idea to talk to us, just send a message to any of us you know, and we can see if you have something to talk about and we have an empty slot, and if it's interesting for the chapter, of course. It would be really interesting.
We have a form, like there is a form that you can find in Instagram or Facebook. You can
May I suggest you add it to the chat in this group too?
Yeah, of course,
Yeah, we
everybody
can,
is
and
in this.
also I wanted to say that we also have a Twitter account from
Right, yeah.
last 2 weeks, and that form is yeah. I mean, you also can follow there if you want to know more and follow the, let's say, our events. And also I think form is there, so
Amazing, amazing.
yeah.
Thank you, guys. Yeah, of course, you are welcome to present for us, and yeah, I'm looking forward to receiving your forms. Thank you so much, and have a great day. See you guys later. Bye.
See ya.
Thank you.
Bye.
Bye.
Thank you, Yousef. It was really nice to hear you from here. Always, I see your presentation during the conferences.